obtain the vibrations on each axis. And everybody has, by the way, such a sensor in his pocket. It's available on a smartphone. So that's basically then the whole pipeline. You have the manufacturing plant and you just get the data in, and what you do is multivariate anomaly detection. And why I want to use neural networks for that, I will show you later. There are two promising publications, and I just want to write a third one. So that's my final goal. So I've written a test data generator because you are not allowed to use any client data. So I'm from IBM, I work in client projects, but if I ask them to give me the data, they don't give it to me. So that's always a problem. So I've written my own test data simulator, which is based on a physical model. It uses the Lorentz attractor model, which is, Lorentz was the inventor of the chaos theory. So you obtain chaotic data, not to confuse with random data. So chaotic data looks like random data, but it follows some patterns, and those patterns I'm able to detect with a neural network. So this can be deployed to a cloud server, and what it generates vibration data following the Lorentz attractor model. So that's a healthy state. That's just plotted the 3 dimensions of the vibrations on a time series, and that's the broken state. If you plot each time series of each axis individually, you obtain something like that. So what you see, it just oscillates between 2 states, and that's the broken state. And what I've done is, in order to get some useful features, I've just transformed that to the time domain using fast Fourier transformation. So that's the healthy state. You see there are some low and high frequencies present in the healthy state, and if you do the same for the broken state, you see that there are more frequencies in the middle, and also the overall energy of the whole system is higher, which is kind of logical. If a bearing is about to break, it will be louder, it will vibrate more, it will get hot. So these are the 2 publications which inspired me. So one is on anomaly detection using an LSTM network, which outperformed all the traditional methods. And as you can see here on the top right hand side, you see here patterns of time series, and always on the bottom you see the anomaly score, and you see that it works pretty well. The same thing has been done using different sorts of algorithms for forecasting. So you see here a forecast of a time series. Blue is actual and red is predicted. The state-of-the-art method used was kernelized regression with an error rate of 8.3. Then they have used the frequency neural network. That's what I will now use. They've transformed the data into the frequency domain and used the neural network. And they've done 2 other steps, deep feed-forward network, which outperformed the frequency neural network, which basically means that the deep feed-forward network has learned a better feature representation than fast Fourier transformation would deliver. And then there's a deep recurrent neural network, which has only 2.8% of error. And the reason why that works so well is because recurrent network and LSTM networks, they remember state, they have memory. And LSTMs have long-term memory. So that's why they perform well. So what I will use today for a demo is a so-called autoencoder. So we have seen that in the talk before. Word2vec is nothing else than an autoencoder, which reduces the dimensionality of the input to a lower dimensional representation. Linear dimensional reduction algorithms are, for example, singular value decomposition and TSNI. Or TSNI, yeah. We talked about it at lunch about that. So that's a non-linear version of dimensionality reduction algorithm, which is quite interesting. And the idea is it sees input data, it maps the input data to the input data as well, but it has a bottleneck of a lower dimensional layer. That means it will just remove all noise, and it will again also learn how to reconstruct data which it has seen before. So if it sees data which is new to neural network, the reconstruction error will increase. And that's basically what I will show you now. So now I have to sit. I will just try to... who cannot see the screen now? Everybody. So no worries. There's a long table. And wireless network. Better? Yeah. Okay. So let's start with the demo. So who cannot read this? Okay. Everybody is starting from row 3. Okay. Oh my God. How
Assuming that we know Java.
Huh? Assuming everybody knows Java. If you know Python, you know Java. Okay. Oh my God. So there are 1,000 parameters to change the font size.
Just type in font size? Or?
Yeah, there are 100 font parameters. Debug. It's a Java editor. Huh? Java editor text font. Okay. 11. Edit. Let's take 33. Apply. Okay. Ah. Yeah.
Okay.
33. So who cannot read this? Everybody. Perfect. Okay. So yeah, shall we start? We start at the main method and we start with the configuration. So you start with the so-called builder, and now where the assembly language versus high-level language part comes in is now, because you don't have to initialize and define any bias or weight parameters. You just straightforwardly define the topology of the neural network. So you add basically a section where you configure global variables, and then sections where you configure each layer individually. And you can, for example, define the activation function globally, but if you find one layer should have another type of activation, then you can just override it. Also, like weight initialization algorithms, updaters, so you can define the learning rate to be decaying over time based on certain properties. So everything what is there you have to implement manually is only a parameter. So for example, if I open that, it's still small, but you see there are hundreds of methods where you basically define the configuration of each layer. So that's the configuration. The configuration can, as I said, used to generate a single node implementation or implementation of Apache Spark. And what I then basically do, I train. So net.fit just uses the data to train. So when I call net.fit with features and labels, then the weights are updated based on my configuration I put there, like learning rate and dropout and whatever. So if I call net.score, it's only scoring. There's no parameter update taking place anymore. And what I then do is I train. So let's do that. So the console is a bit small, but you see here that's the error which is decreasing. If you don't like system out print line, you can use another cool thing for displaying the progress of your learning.
Control O.
That's a graphical way of doing it. So you see here the learning rate is falling, sorry, the error is falling and converging, which is a good sign. It's still very high, but if I change the topology of the neural network or if I obtain more data, it will be lower. But it's sufficient to create my anomaly detector because the scene data has an error of 8.8 times 10 to the power of 8. And if I score it with the unseen data, it has an error of 2 times e to the power of 10, so 100 times higher. And that basically is my autoencoder, and that's perfect because I'm finished and we have 2 minutes for questions.
Okay. Thanks, speaker again.
Yeah, I have a good question. On my one, how complete is the set of basic units you can have in DeepLearning4J? Do you have convolutional layers? Do you
Yes, you have convolutional layers, you have LSTM layers, recurrent layers, yeah, everything.
And they all go then to CUDA and work faster now?
Yeah, because the layers using ND4J and ND4J, all operations on ND4J can be accelerated using GPUs.
And let's say if you want to do something really crazy, then can you also do it? Or?
Yeah, you have to implement your own layer, of course.
Okay, but you can implement your own layer, then with the gradient then or something like this.
Yeah.
So it's not doing like building a tree like TensorFlow does, and then doing out of it, but it's somehow like Torch or something like this. You have to manually implement the gradient and then do this.
You have to manually implement it.
Yeah, maybe. No.
Do you know anything about the performance comparison with other frameworks?
I only know that ND4J has more than double of the performance of NumPy without GPUs. So it should be reasonably fast, but I haven't tried. I have to, because next week I'm giving a talk on how it performs on a cluster of GPU machines, then I know more.
But the single operation, if they are running on the GPU, if they are now translated anyway into the CUDA stuff, and it doesn't really depend on the framework. So
Did you experiment also with different patterns? Because what you have shown, it seems pretty obvious. You have one pattern is like this, and the other one is just the shifting of it. So it's a pretty significant difference. Did you try something that's so obvious?
No, I have to try. But what I then will do is I will use the LSTM instead. So that's a quick and dirty.
No, but this doesn't change that the input data is kind of obvious.
Yeah, but I will, if I try with other data, I will then try it with the LSTM. Because if you've seen the publications, the error of the LSTM is far lower than a frequency deep learning network. It's not even deep learning, than a frequency neural network. So I will anyways go for a LSTM then.
Okay. I think we have also now a little poster session, and we'll be around and you can ask yourself. Maybe let's thank the speaker again first. It's the very same floor. There's now coffee served, and the poster